fine. In the last class, we have started with the non-coherent detection schemes. So we have started with the binary Bfsk. Okay, so I have shown you how the binary Bfsk will be detected using non-coherent methods. Okay, so always you have to remember the difference between coherent and non-coherent. Okay, coherent, as I was mentioning, even at the receiver end, you'll be using the same carrier as the transmitter. Whatever carriers you are using at the receiver end, sorry, transmitter end, the same carriers will be used at the receiver end also. Okay, so that is said to be the coherent detection. Okay, but when it comes to the non-coherent detection, we'll not use same carrier. Instead, we'll use the matched filters. Okay, so instead we'll use the matched filters. Okay, so we have seen Bfsk generation, the normal generation, how whatever we have studied before, the same diagram have drawn once again. Okay, then comes Bfsk non-coherent detection. Okay, non-coherent detection of Bfsk. So whenever the term non-coherent will exist, you can just check matched filter will be used. So if you just check here, I've used the matched filter. So as I'm using two carriers at the transmitter end, I need two matched filters. One filter, it has to match to cos 2 pi f1t, and the other filter it has to match to cos 2 pi f2t. Okay, here additional carrier need not be used, and it need not be synchronized with the carrier what you are using at the transmitter end. Then after that, envelope detector. Okay, so envelope detector, it will detect the envelope of the signal. Okay, after the matched signal, whatever signal you're getting at the output, it will take the envelope of that particular waveform. Okay, so from the and taking the envelope, what we'll do, we will sample it in the sense, we will not take, see, let me consider this is what my signal is. Okay, and this is the envelope. Okay, so this envelope output will be like this. Okay, so this envelope output, it won't be dotted line, it will be like whatever shape it is having. Okay, so what we'll do, we will not take all the values, but only at a particular instant. Okay, t is equal to tb, it will be sampled. Okay, so only this sample will be there, and the rest of the signal will not be there. Okay, so that is what the use of the sampler. Okay, so here t is equal to tb, this is nothing but the sampler. Okay, so it is like a switch. Okay, only at that point it will just close, so that value will be taken. Okay, so that value, whatever envelope value you're getting at t is equal to tb, that is nothing but L1 in the upper comparator and L2 in the lower comparator. If L1 is greater than L2, the next, that L1 and L2 are given to the comparison device. Here what it will do, if L1 is greater than L2, it will take the decision in favor of symbol 1. If L1 is less than L2, it will take the decision in favor of 0. Okay, so this is what all related to the non-coherent detection of Bfsk. Okay, so for the exam point of view, either internal or external. Okay, Bfsk, most of the question papers they have asked. Okay, so that is all related to the Bfsk. And see, as I've already mentioned, you need not derive the expression for average probability of error, but you can just remember this equation. So what you people can do, take out a sheet and make sure that you write all the equations related to this particular module. Any module you take, try to list out all the equations, so that it will become easy for you to memorize it. Okay, fine. This is all related to the Bfsk. Okay, now coming to the next non-coherent detection methods. So you people have already learned Bpsk. So Bpsk non-coherent detection I need to do. Okay, so Bpsk generation will be normal, how we were generating. So if you just want to see the generation, once again I'll just show you, because yesterday I really felt so bad. You people were not even responding, and like, I don't know whether you have clearly understood or not also, I didn't get to know. So let me just show you the non-coherent detection of your Bpsk. Bpsk generation. So see here, generation of Bpsk. This is what the generation. Okay, so normal generation will remain same only. What we are doing, binary data sequence, it is given to the polar NRZ level 2 encoder. In the sense, like what it will do, if I have a 0, it will encode with no amplitude. If it is 1, it will encode with root EB. Okay, so this is nothing but it is converting the binary data to the pulse signal. Okay, So this signal, whatever I'm getting, is also said to be the pulse amplitude modulated signal. Okay, so this is what I will be getting here, and this is given to the product modulator. Okay, product modulator in this is, it is nothing but just the multiplier. Okay, so this B1 and this pi1 will get multiplied here, and I'll get the binary PSK signal. Okay, so here what it will do, if I have 0, 0 will get multiplied with Bpsk, no? Okay, so here what it will do, it will take polar in the sense root EB for symbol 1 minus root EB for symbol 0. Okay, so what it will do, if I have a symbol 1, then the input to this product modulator will be root EB. Root EB into phi 1 of t will give the S of t signal when for symbol 1. Okay, when I have symbol 0 as my binary data, then this polar NRZ level, it will convert it to minus root EB. So minus root EB will get multiplied with phi 1 of t, so that you'll get the output as S of t for your binary 0. Okay, binary 0. Okay, so S of t equation will be nothing but, I have specified every equation here. So S of t equation is nothing but root 2 EB by TB cos 2 pi FCT for symbol 1, and minus root 2 EB by TB cos 2 pi FCT for symbol 0. Okay, so if you just name this as S1 of t, and this is nothing but minus S1 of t. Okay, so that's all the difference. Okay, what will happen in the Bpsk, it will have the phase shift. When you have 1, the same signal will be transmitted, cos 2 pi FCT, the same signal will be transmitted. When you have a 0, there is a phase shift. Okay, so that phase shift is denoted by minus. Okay, so S of t is nothing but S1 of t for symbol 1, and it is equal to minus S1 of t for symbol 0. Okay, so the same thing I have explained here also. I don't know, I really don't know how many of you have understood. Okay, so here, whatever I have explained, see the transmitter related equations I've just explained here. Okay, fine. So this is what the generation. Coming to the non-coherent Bpsk. Non-coherent Bpsk. So as the name implies, I should not use any carrier at the receiver end. Okay, so here I've not used, instead of using the carrier at the receiver end, what we are doing is we are taking the bit is delayed, and it is given to the product modulator. Okay, or multiplier. You can either call it as product modulator or multiplier. Okay, we are giving it to the multiplier. Okay, so what is happening here, if you observe delay TB in the sense, as I was specifying, each bit duration is TB seconds. Each bit duration is TB second. Okay, now what I'm doing, I'm delaying it and I'm giving it to the product multiplier. Okay, so what happens, Bi and Bi minus 1. Okay, so if Bi and Bi minus 1 are same, both are same in the sense, even this is 0 and this is 0. Okay, so this is 0 in the sense, S1 of t multiplied with S1 of t, it will be equal to S1 square of t. Okay, that you're integrating. Okay, after integrating, you're sampling it. Okay, so when you sample it, your L value will be some constant value like this. Okay, so that is given to the decision making device. Okay, so this decision making device will give either symbol 0 or symbol 1 based on this L value. Okay, so if L value is greater than 0, then it will take as binary 0. If it is less than 0, it will take as binary 1. Okay, so that is for when Bi and Bi minus 1 are same. Either it is 1 1 or 0 0, it doesn't matter, because here S1 of t for 0 you have S1 of t, for 0 you have minus S1 of t, for 1 you have S1 of t. Okay, so what will happen, 0 in the sense, here also I'll get minus S1 of t, and here also I'll get minus S1 of t. Both will get multiplied, so minus into minus, it will become plus. Either you take 1 1, here 1, here 1. Okay, so what happens, 1 1, it is given to the multiplier. So 1 in S1 of t multiplied with S1 of t, you'll get S1 square of t. In both the cases, the output of the multiplier will be same. Okay, so that is the reason, so either Bi can be 0 0 or Bi can be 1 1. This is how the detection will happen. Okay, fine. Next, both are different in the sense, if Bi is 0, Bi minus 1 may be 1. Bi minus 1 may be 1. If Bi is 1, it is 0. Okay, in that case, what will happen? I'll get the negative sign because s1 of t into minus s1 of t. Okay, s1 of t into minus s1 of t. So I'll get a negative sign. Okay, then square of my s1 square of t. Okay, that is given to the integrator. Okay, so I'll get some signal. Okay, when you sample it at t is equal to tb, you'll get L. That L value will be less than 0. Okay, so if you have minus 2 tb, then the decision will be in favor of symbol 0. Okay, so this is how the non-coherent Bpsk can work. But there is a problem here. The problem is, if see here what I'm doing, I'm delaying the bits and I'm giving it to the product modulator. So it is purely depending on the received signal. Okay, this bi is nothing but whatever is transmitted, that is getting received at the receiver end. So whatever bi corresponding equation, 1 second. Whatever bi corresponding equation I have, okay, so that equation I'm getting it from the transmitter end. Okay, so what happens here, if let me consider the present bit bi is, instead of it is transmitted as 0, but the receiver, if it has received as 1, what happens? It will be error. Okay, and the output will not be correctly decoded. Okay, in the same way, and every time whatever bits I'm receiving, it is the error in the detection is happening. The reason behind that is, since I'm delaying it and I'm giving it to the product modulator every time. So let me just show you. Here let me consider 0 1 0 0 something like that. It is transmitted first. Initially this is bi and this is bi minus 1. Let me consider this has gone wrong. Okay, so what happens, these two will based on these two symbols, instead of 0, let me consider I've got as 1. So based on this these two, the output will be generated. Again, delayed version. Now this will become bi minus 1 and this will become bi. Okay, so delayed version. So what will happen here? Every time the output is getting error. Okay, the output is getting error because of wrongly detecting 1 bit. Even if you detect 1 bit wrongly, this error is propagating. In the sense, like the error is continuously in the received finally estimated signal. Whatever estimated signal you have here, it is continuously erroneous. Okay, erroneous in the sense it is continuously, like whatever it is decoding, it is all error. Error is getting propagated because of 1 bit wrongly detected, it is propagating. So that is what the disadvantage of non-coherent Bpsk. So in order to avoid this problem of like propagating the error signal, we will not go with non-coherent Bpsk. Okay, even though I have drawn and like I've shown you it's working, we will never ever go with non-coherent Bpsk because of this disadvantage. Okay, so what we'll do, we'll go with the differential phase shift keying. Okay, so non-coherent Bpsk will not exist, so that is the reason Dpsk will go with the Dpsk. Okay, this is said to be the non-coherent version of Bpsk. Non-coherent version of Bpsk. Okay, this is said to be the non-coherent version of Bpsk. Okay, so here again, if I want to have the differential phase shift keying at the detector also, I need to also have the transmitter. Okay, so the Dpsk transmitter is taken in this way. So here what we are doing, instead of if you just take your Bpsk modulator, Bpsk generation. This is your Bpsk generation. If you just observe here, what we are doing, we are directly taking bits. Okay, if I have a 0, that will be encoded either 0 or 1, and then that is given to the product modulator. That is given to the product modulator. It is multiplying with root 2 by tb cos 2 pi fct, and it is giving me the binary Psk signal. But here, what we are doing in the Dpsk, we are employing the differential encoding scheme. Differential encoding scheme. Differential encoding scheme. Here what we are doing is we are using an additional gate. Okay, an additional gate is used here. Okay, so here if you just observe the difference, here directly binary data is directly given to polar in RZ. Okay, but here what we are doing, we are not giving in that way. We are first differentially decoding the data, and that is given to the amplitude level shifter, which is also nothing but here polar NRZ format. Polar NRZ format. Okay, so instead of giving it directly to the polar NRZ, we are differentially encoding the data and we are giving it to this, so that the advantage of doing this is whatever error propagation was happening in non-coherent Bpsk, it will not happen here because of this in differential encoding scheme. And here how it is happening, we need to check now. Okay, so see here, this is a binary data. This is a transmitter end. Okay, so just understand very carefully. Bi is a binary data. Binary data in the sense whatever, like I am speaking. So whatever information what I am speaking, it will be converted to digital data. So that will come here. Okay, and if you observe, this is nothing but the XNOR gate. XNOR gate. Okay, so generally the XNOR gate will be in this way. Okay, so A and B are the inputs. The output will be A exclusive or B. Bar. Exclusive NOR symbol B. Okay, the equation for this is nothing but A bar B bar plus AB. Okay, so this is what the output of this year, output of your XNOR gate. Okay, so here we are using that. Okay, and if you observe, one input is directly the binary data. Whatever the second input to this XNOR gate, it is not given directly. It is given from the output. There is a feedback here. Okay, from DI, it is given back to the XNOR gate. Okay, so DI is generally obtained as DI is nothing but BI inputs XNOR operation between the inputs BI and DI minus 1. Okay, are the inputs to this XNOR gate. Okay, so DI is nothing but, we can write in this form, it is nothing but BI complement DI minus 1 complement plus BI DI minus 1. Okay, so if you just check here, initially you may ask, mom, initially when I have got the first bit here, what will be the data here? You can either take a 0 or a 1 as reference. Okay, by taking either a 0 or by taking either a 1, you can provide DI. Okay, so this is what your differential encoding scheme. So what here, let us first study the truth table. So A, instead of A you have BI, instead of B you have DI minus 1. These are the inputs. Okay, and outputs. Truth table, I'm writing the truth table. Okay, so in the truth table I'll have the relationship between input and output. Okay, so here if you just observe, I have two inputs. So two inputs, I'll have four combinations: 0 0 0 1 1 0 1 1. Okay, and BI XNOR with the DI minus 1. Can anybody tell me the output values of your XNOR operation? Truth table. When I'll have 1, then I'll have 0.
When there are same bits.
When there are same bits, the output will be 1 or 0.
1.
1. Okay. So it is not the same bits. It is like the number of odd number of ones, like that. Okay. So odd number of ones here. I don't have odd number of ones. So even number of ones, it will be equal to 1. Okay. So 0 0. XNOR gate. Okay, so based on this only this will work. Okay, so if based on this, if you just observe BI and DI minus 1. Okay, BI and DI minus 1. Just check carefully. BI and DI minus 1. If BI and DI minus 1 or 1 1, 0 0, the output is 1. Okay, so it means that if BI is equal to DI minus 1, what happens? That is what we need to understand here. Okay, so if bi is equal to di minus 1, your di bit will be equal to 1, right? Because either you take 0 0 0 0 or 0 1 1. Okay, in both the cases the output is 1. Okay, so if bi and di are same, then the output will be equal to 1. If bi and di are different, then the output will be equal to 0. Okay, so di value is depending on input bits, bi and di minus 1. bi bi and di minus 1. Okay, based on if bi and di minus 1 are same, then the output will be equal to 1. If bi and di minus 1 are different, then the output will be equal to 0. Okay, so this 1 I have, so that 1 is given to the level shifter, and as I've already mentioned, 1, if I have a 1, it will be encoded as root eb. If I have a 0, it will be encoded as minus root eb. Okay, so that is given to the product modulator, and the output will be Dpsk signal. Okay, so this is the generation. This is how we are generating the Dpsk transmitter. So let me just give you in the form of tabular column also, like how what will be the phase that you are getting. See here, I'm just telling you orally that when bi and di minus 1 are same, the output is 1. When bi and di minus 1 are different, the output is 0. Okay, so and if I have a 1, I'll get root eb. If I have a 0, I'll get as minus root eb. So this I will just represent in the form of a tabular column, so that the Dpsk signal, either, let's see, if you observe again, I have 180 degrees phase shift only. Okay, but this phase shift corresponds to differential data, not the direct binary data. That is what the difference. So let me just take the tabular column. Okay, for let me take bi as 1 0 0 1. Randomly I'm taking 0 0 1 1 something. Okay, now I need to this with di minus 1. Di minus 1. Okay, so let me assume that let me assume the di differential encoded data, di initial bit, I'm considering it as 1. Okay, so initial bit I'm considering it as 1. Okay, so it means that di minus 1 will be 1. Okay, so what is let me just write it properly. Wait, I'll not write this. I'll write this later. di differential data. So if you just observe the di output is depending on bi and di minus 1. So as I've already mentioned, you can either take 0 as my initial bit or 1 as my initial bit. Okay, so let me just take 1 as my reference bit and let me do it. So 0 0, I need to perform XNOR operation. Now this is nothing but your d minus 1, right? Hope you people are following. Hope you people are following.
Yes, ma'am.
So here what I'm doing, I've taken BI binary data. This is my binary data. Okay, so whatever I'm speaking, it is converted to binary. Let me consider this is what the binary data. Now what I need to do, I need to find out what is DI output. Okay, if I want to find DI output, I need to know initial bit, because if you observe, the delayed version of DI is given as an input to the XNOR gate. Okay, so now I can either assume it as 0, I can assume it as 1. I can take as 1 or 0, anything I can take. You can just check anything you can take. Okay, so 1, let me take 1. Okay, 1 as my reference bit. Okay, so this is my di minus 1 bit. Now what I need to do, I need to perform XNOR operation between this bi and di minus 1. So bi and di minus 1, 1 and 1, 1 and 1 according to the table. 0 0, it is 1, 1 1, it is 1. For 0 1 or 1 0, the output will be equal to 0. Okay, so 1 1 exclusive exclusive NOR operation between 1 and 1. So the output will be equal to 0. Okay, again I need to perform. Sorry, it is 1, no? 1 and 1. See, this is very, very important. Even in the exam, they may ask you represent the phase of the, they will give you the sequence. We'll do some problem related to that also. They'll give some problem and they'll ask you to show the Dpsk operation, Dpsk waveform. In that case, you should be in the position to do it. Okay. So 1, 1, 1, XNOR operation, XNOR operation. So 1, 1, the next bit will be equal to 1. Okay, again this bi will get XNOR operation with this. So 0, 1, 0, 1, the next bit will be equal to 0, 0, 0, the next bit will be equal to 1, 1, 1, it will be equal to 1, 0, 1, it will be equal to 0, 0, 0, it will be equal to 1, 1, 1, it will be equal to 0, 1, 0, it will be equal to 1.
1, ma'am.
Here also 1, no? Here also 1, yeah. Here also it is 1. Okay, 1, 1, it is 1. 1, 1, again it is 1. Okay, so this is what your DI data. Okay, DI data in the sense this is what I'm getting. So as you know that this polar NRZ, it will convert, if I have a 1, it will convert to root EB. Root EB in the sense no phase shift. Okay, root EB, no phase shift, 0 minus root EB. So there is phase shift of pi. Okay, or 180 degrees. So here I need to mention the transmitted phase. Okay, if I have a 1, no phase shift, so 0. If I have a 1, again no phase shift, 0. If I have a 0, there is a phase shift, right? 0, for 0 there is a phase shift, right? So it is encoded with minus root EB. Okay, so minus root EB is nothing but phi. Okay, again 1, no phase shift, 1, no phase shift, 0, there is a phase shift, phi, 1, no phase shift, 1, no phase shift, 1, no phase shift. This is what this is how the phase is transmitted in the Dpsk signal. This is how the phase will be transmitted in the Dpsk transmitter. Okay, so if you just want me to draw the signal, it will be like this. Okay, so di. Okay, di. Let me just do it with a problem. Okay, not now. Let me explain this first. Okay, after that I'll go to the problems, and that time I'll draw and show you the diagram. Okay, so your Dpsk signal, finally the Dpsk signal is given as Dpsk signal, whatever I am getting here, whatever I'm getting here, let me represent it with S of t. Okay, so that is given as S of t is equal to root 2 EB by TB cos 2 pi FCT. Okay, because this is for symbol 1. Symbol 1. Okay, symbol 1, or I will write as when di is equal to 1. Okay, or it will be minus root 2 EB by TB cos 2 pi FCT when di is equal to 0. Okay, so this is what is happening here, because I'll get root EB. Let me consider for symbol 1. Okay, root EB. So it will get multiplied with this carrier, and I'll get the Dpsk signal. Let me consider it is 1 0. 0, it will take as minus root EB. So minus root EB will get multiplied with root 2 by TB cos 2 pi FCT, and I'll get the Dpsk signal. Okay, so that is what your representation of Dpsk signal, and here it is depending on di bit. Okay, based on the di bit I'm getting the output signal. Okay, so this is all related to the transmitter. Okay, any doubts here? Any doubts here? Quickly.
No,
No, ma'am.
Next, Dpsk receiver. Okay, Dpsk receiver. So here Dpsk receiver, it is non-coherent. Okay, non-coherent Dpsk receiver. Okay, non-coherent Dpsk. So x of t will be the received signal. So x of t, how I'll get x of t? This s of t will be given to the channel. Channel will add the noise, and then I'll get x of t. Okay. Now let me assume that I'm passing this x of t through the band pass filter. Okay, band pass filter. The use of the band pass filter in the sense it will allow only certain frequency ranges. Okay, so let me assume that this bandpass filter is eliminating the noise. In the sense, I'm considering that noise components are very high, and when I'm passing it through the bandpass filter, I'm just getting S of t signal only. Okay, S of t signal only. And here, as I've already mentioned, we should not use the additional carrier like this. What was the carrier? It was 2 by t cos 2 pi fct. If I use like this, it becomes coherent version. Okay, so what I need to do, I should not use this. Okay, instead of using this, what I will do is I will take the same. I will delay the signal and I'll take the same signal. Delay with the TB. I'm giving it to the multiplier. Okay, then after the multiplier, I'll give it to the integrator. 0 to TB dt, and then I'll sample it. Sample it. T is equal to TB. Okay, if you just observe this circuit and this circuit is same only. Where it is? Here, whatever I have explained you here and whatever I'm explaining you here, it is the same circuit only. Okay, but only difference is here I'm not transmitting the binary data, I am transmitting the differential data. Okay, so L, and here I'll have the decision device. Okay, and if L is greater than 0, 1 will be chosen. If L is less than 0, 0 will be chosen. Okay, so here if you observe, it is delayed. Okay, delayed in the sense here I'm transmitting DI. Okay, DI bit is transmitted. Okay, if DI is equal to di minus 1. So here what is happening, I'm getting the equation corresponding to di and di minus 1. Okay, if di and di minus 1 are same, then what happens here, di and di minus 1 are same, di and di minus 1 are same. Okay, it means that I may get either both this as inputs to the modulator, sorry, this one multiplier. Okay, both I'll get as this only to the multiplier, or I'll get both this only to the multiplier. So what happens, this multiplied with the same, I'll get positive. This multiplied with the same, I'll get more positive. Okay, so I'll get as 2EB. See, the output here will be 2EB when this is di and this is di minus 1. Okay, equation corresponding to di, and here it is equation corresponding to di minus 1. So when you multiply both of them, and I'm assuming the condition when di is equal to di minus 1. When di is equal to di minus 1, the output of this product modulator I'll get as 2EB. Let me write here, 2EB by TB cos square 2 pi fct. Okay, in either cases, either di can be a 0 or a 1, whatever it might be. If di is 0, di minus 1 is also 0. If di is 1, di minus 1 is also 1. Okay, so now you will just integrate it from 0 to TB dt. Okay, then after that, if you sample it, you'll get as EB as the output. L value will be EB. Okay, so if L is greater than 0, so here in this case L is greater than 0. Okay, in that case it will be taken as 1. Okay, if di and di minus 1 are same, then the output will be in favor of 1. Okay, now let me assume that if di is not equal to di minus 1. Okay, if di is not equal to di minus 1 in the sense, see here, if you observe, this is di equation and this is di is equal to 0 equation. So di and di minus 1 are not same. In the sense, if I have a 0 here, I may have 1 here. If I have a 1 here, I'll have a 0 here. So any case, if you consider this equation and this equation will get multiplied with each other, so that I'll have as minus EB as my L value. Okay, so square it, integrate it and sample it, your value will be equal to negative here. You'll get negative value. Okay, so negative value when L is less than 0, the decision will be taken in favor of symbol 0. Okay, so this is all related to the Dpsk receiver. Any doubts here? Quickly. Any doubts here? Okay, so the average probability of error for your Dpsk is given by, here also you need not calculate, as I was mentioning, a half exponential minus EB by N naught. Okay, this is nothing but half e power minus EB by N naught. Okay, both mean the same only, don't get confused. Okay, so this is the average probability of error of your Dpsk. Now, this is what the non-coherent version. Okay, so here what we'll do, we will also study the coherent version. Why I am specifically teaching you this, and this is very, very important. Whatever I'm doing now, it is very, very important. Okay, so in the exam, if they ask you to just write Dpsk transmitter and Dpsk receiver, then you can go ahead with these two. See, understand the question correctly, okay, because there are no direct question won't be given. Okay, so whatever we have seen here, it is non-coherent Dpsk. Okay, so non-coherent Dpsk, when they ask you just explain Dpsk transmitter and Dpsk receiver, you have to explain this one and this one. Okay, this one and this one. Okay, but specifically when they ask you to explain optimum receiver or coherent detection of Dpsk, then you need to explain this one only. Okay, I will repeat, when they specify the word optimum receiver of Dpsk, you need to explain whatever I'm going to do now. Okay, the reason behind this is correlation receivers, in the sense like if you are synchronizing the carrier and using at the detector end, that will give you the more optimum output. Okay, more optimum in the sense that is the best. Okay, the nothing will be more than that. Okay, that is what the optimum means. Okay, so here I'll just give you the optimum receiver. So as optimum receiver is nothing but the coherent detection only. Okay, so in the coherent, when you do the detection coherently in the sense in synchronized with the carrier, then only it will work it will give you the optimal result. Okay, so that is the reason if they ask you to explain optimum receiver of Dpsk or coherent detection of Dpsk, then you need to go ahead with this diagram. Okay, so here what I need to do, I need to use the carriers. Okay, not the matched filter. I need to use the carriers, or I'm not even taking the delayed version. No, I'm directly using the carrier. Whatever carriers I'll be using at the transmitter end, the same carriers I need to use at the receiver end also. So here this receiver, whatever I am designing, it is the optimal quadrature receiver. Optimum quadrature. Always the word quadrature implies that you'll be using cos and sine. Okay, both will be there. Okay, cos and sine. Cos is in phase component and sine is quadrature component. So here to the upper multiplier, you'll get cos 2 pi fct, and to the lower multiplier, you'll get sine 2 pi fct. Here the additional carrier is used. Okay, so what we'll do is, if we have cos 2 pi fct, from you take it minus 90 degrees phase shift that, then you'll get sine 2 pi fct. Then after that, integrator 0 to t dt, here also 0 to t dt, and then give it to the delayed version. It is given to the multiplier once again, multiplier. Okay, here also we'll give it to the multiplier. Sorry, the delayed version is given to the multiplier. Here it is delay TB. Delay TB. This is the optimal receiver. Okay, and give this to the adder. Okay, because if you just recall your Bpsk signal. Okay, so generally Bpsk signal will be denoted as Si of t is equal to root 2 EB by TB cos 2 pi fct plus theta. Okay, theta is some angle. Okay, so this is nothing but for the phase shift keying techniques. This is what the general equation. When you expand it, you'll get cos 2 pi fct and you'll get sin 2 pi fct. Okay, so that is the reason you need to add this term and this term. That is the reason I'm giving it to the added like this plus plus, and then I'll get y as my output. Okay, so that y variable should be given to the decision device, which will be compared with threshold value. Okay, let me take the threshold value also 0. So if y is greater than 0, it will choose 1. If y is less than 0, it will choose 0. Okay, that is how it will operate. See, this entire thing is same only as you were using in your this Dpsk receiver. Okay, but only thing is here additional carrier you're using. Okay, instead of delaying it and giving it to the multiplier, here you're additionally using the carrier. Okay, so that is what will happen. So the same thing, so whatever value you'll get from this, it is given to the multiplier, and the delayed version of the same bit, if it is di here, it is di minus 1. Okay, that is given to the product modulator, and then that value is given to the summer. From the lower part also it is given to the summer. Both will get added and they'll get y value. So when y value, based on the y value, it will be decided either in favor of symbol 1 or symbol 0. This is a coherent detection of your Dpsk. Okay, Dpsk, coherent detection of Dpsk or optimum receiver. Okay, x of t from x of t only, this all will happen. Okay, and if you try to plot the signal flow graph here, signal space diagram, you'll have as a cos theta. See, from this, if you just expand, you'll have a cos theta and a sin theta as one pair, and a cos theta minus a cos theta and minus a sin theta for the other pair. Okay, so that's what this is for 0 degrees, and this is for 180 degrees. 180 degrees, it will have the negative phase. Okay, when you try to plot the graph. Okay, here I can either take as xi, xq, or as usual we were taking as phi 1 and phi 2. Okay, anything you can take. This indicates it is just the in phase component and the quadrature component. So one point you'll get here and the other point you'll get here. Okay, so distance between this and this will be same. Okay, so this is the signal space diagram of your optimal receiver. Okay, so this is all related to your Dpsk. So now let me just now take one problem and show you how to plot the waveform and how to get back the output signal from the graph. Okay, so take down the hope you people have understood, right? Is it clear to all of you?
Yes, ma'am.
Okay, fine. Okay, so now let us do one last problem. Not last problem, we'll do. So for this, write the question for the binary sequence. For the binary sequence given, find for the binary sequence given as 1 0 0 1 0 0 1 1. I think I've taken the same sequence only, right? 1 0 0 1 0 0 1 1. Okay, fine, let it be. For this I'll show you how to decode it. Okay, so bi is the binary data. Okay, so for the binary sequence given as this, illustrate the operation of Dpsk. Illustrate the operation of Dpsk. In the sense, here what you need to do, starting from the differential encoding, transmitting, receiving, everything you need to explain. Okay, so bi is a binary data 1 0 0 1 0 0 1 1. Okay, now I need to first differentially encode it, right? See, if you just see here, transmitter, I need to differentially encode it. Okay, so in order to differentially encode it, I will take a di. Let di minus 1 bit be 1. Okay, so 1 1, this will become 1 0 1 0 0 0 1 1 1 1 0 1 0 0 0 1 1 1 1 1 1 1. This is what your di. This is a differentially encoded data. Differentially encoded data. Okay, now what will be the phase transmission? phase transmission, because based on this DI values, it is either giving me based on your DI values, it is either giving me 1 or it is either giving me 0. Okay, and that is given to the product modulator. So 1, if it is 1, it is root EB. If it is 0, it is minus root EB. Okay, so when it is 0, it is introducing 180 degrees phase shift. Okay, so phase transmission. Okay, phase transmission or phase of Dpsk. So if I have a 1, no transmission, 0, 1, 0, 0, 180 degrees, or I can even write as 5. Anything is fine. 1, 0, 1, 0, 0, 180 degrees. 1, 0, 1, 0, 1, 0. Okay, so this is the phase of the Dpsk signal. Okay, and this will be transmitted to the receiver. Okay, so this is what your receiver. So this whatever I have generated, this SI of t, it is transmitted to the receiver. And here, as I've already mentioned, I'm using the bandpass filter, which is eliminating the noise, and it is giving the input to the multiplier. Okay, so okay, so what will happen? See, DI and DI minus 1. Let me write the DI minus 1 also here. DI minus 1. DI minus 1 in the sense from here it will start, right? So 1, 1, 0. See, from this only I'm writing. Okay, so DI minus 1 is nothing but the delayed version of this. Okay, so 1. First I'm writing 1, 1, 0, 1, 1, 0, 1, 1. This is a DI minus 1 sequence. Anybody have doubt here? Please let me know. You can either write 180 degrees or 5. It is okay. Okay, so this is DI minus 1. So why I'm writing this DI minus 1 specifically? Because if you just check the receiver, okay, the output of this is depending on DI and DI minus 1. Okay, so that is the reason I have written this DI minus 1. So anybody have doubts with this line? If you have any doubt with this line, please let me know quickly. I will just wind up because oh, it's already 9:48. Let me just do this problem and wind up. Okay, fine. Are you understanding?
Yes, ma'am.
Okay. So here, if you observe, this is DI and DI minus 1. Okay. So what we are doing, if both are same, I will have the positive value, right? If both are, this is my receiver. If DI and DI minus 1 are same, in the sense here also plus and here also plus, or here minus, here minus. If both are same, the output, whatever L value I'm getting, it is positive. Okay. So if it is not same, I'll get a negative value, as I've already explained. L value will be negative. So let us write based on this two lines. Let me write the phase shift. What is it? Phase comparison. Phase comparison. Phase comparison. Here 1, 1. So both are positive. So no phase change. It will be plus. Okay, 0, 1. So minus 1, 0. So it is minus 1, 1 plus 0, 1 minus 1, 0, 1, 0, 1, 0. So it is minus 1, 1. It is plus 1, 1. It is plus. Okay, so this is a phase that will be compared. This plus minus minus plus indicates the L values. Okay, whatever at the receiver I'm getting, no, that L values. Okay, then comes see, from based on this L, either it is positive or negative. That is what it indicates. Okay, so what I need to do, I need to detect or estimate the binary data. Estimate the binary data. Okay, for the estimating this binary data, if I have positive value for L, it will be encoded as 1. If I have a negative value for L, it is encoded as 0. So negative 0, 1, 0, 0, 1, 1. Okay, so if you just observe, the transmitted bits and the estimated bits are same. See, 1, 0, 0, 1, 0, 0, 1, 1. Here 1, 0, 0, 1, 0, 0, 1, 1. Okay, so this is how the detection will happen. And let me just draw the diagram for the same. 0, 1, 0. See, I'm taking the 1 second. Dpsk signal. Let me just draw the Dpsk signal first. So what was the Dpsk signal? Can anybody has written 1 1 0 1 1 0 1 1 1. This is the Dpsk signal. Di value. Di. Where is that? Di. Di 1 1 0 1 1 0 triple 1. 1 1 0 1 1 0 triple 1. Okay, fine. This is a di bits. Okay, based on this di bits only, I'll get my Dpsk signal. Okay. Okay, so based on my Dpsk signal will be like for 1, I'll have no phase shift. For 0, for 1 no phase shift. For 0 there will be phase shift. For 1 no phase shift. For 1 no phase shift. For 0 there will be a phase shift. For 1 no phase shift. No phase shift. No phase shift in the sense it will be in synchronized with that. 1 no phase shift. 1 again no phase shift. This is what my Dpsk signal for the given diagram. This is what the Dpsk signal. Okay, now I will also mention di minus 1. Di minus 1 is nothing but 1 1 0 1. From this only I'm writing. This is my di minus 1 bit. Next to this will become di minus 1. So that is the reason I'm writing it as 1 1 0 1 1 0 1 1. Okay, so for this again you have to draw the diagram. So 1 no phase shift, 1 no phase shift, 0 phase shift, 1 no phase shift, 1 no phase shift, 0 phase shift, 1 no phase shift, 0 or 1 again no phase shift. Okay, now I need to multiply these two, di and di minus 1. Okay, so when you multiply it now, let me just show you. See here, positive waveform is getting multiplied with positive waveform. So I'll have positive only from here to here. Again here, negative getting multiplied with negative. So I'll have still positive. Next, the second one, negative getting multiplied with positive. So I'll have the negative waveform. Positive getting multiplied with negative. So negative. Just I will draw the diagram. You people can check it once again. I'm going a little fast. I'm sorry because madam has already started the meeting. Okay, so for this I have to mention the see here I've got complete positive. Here I've got negative, negative, positive, negative, negative, positive, positive. So when you decode it or estimate it, this will be 1 0 0 1 0 0 1 1. Okay, so this is what the binary sequence and the complete operation of this is nothing but here received output or decoded output or estimated output. So this is how the complete operation of Bpsk is happening. Okay, so there are two more problems. It's direct substitution only. So as I've already posted you the notes, you can just go through those questions. Okay, if time permits, tomorrow I have to start fourth module. Okay, because hardly I have got 2 more classes. So I will take those 2 classes on fourth module. Okay, so there are 2 more problems which are given. You can just go through it because it is just what what is the question is they have given Bfsk related problem. Okay, they'll say that they'll ask you to compare this Bfsk average probability of error for the coherent detection and non-coherent detection. That is what they've asked. Okay, so tomorrow I'll just brief you. Okay, that's all for now. You people can go to the other class. I'm sorry, really sorry, because I was at the end, I could not stop also. Okay, you can leave the class now. Thank you.
Thank you.
Thank you.